Okay, so last time we started talking about hardware and how to analyze different hardware systems, and we briefly touched upon hardware efficiency as well. So in this lecture, we'll continue with hardware efficiency, but first let's do a very quick recap of hardware analysis metrics. So the first thing we talked about was performance. So I'm hoping. And the unit that we used for performance was, flops per second. So flops per second. So the number of floating point operations that my hardware is capable of doing in the best case per second. And then the other thing was memory. And of course, memory has many parameters, but the main thing that affects my performance that we talked about was the memory bandwidth. So usually in some kind of bytes per second, right? So maybe gigabytes, terabytes, whatever it may be. And and that's kind of on the hardware side. So just comparing the peak performance of different hardware to each other. On the other hand, we said on the workload side, we have this interesting metric called operational intensity. Op intensity. So, so what is this? This is the number of operations per unit of memory that I need to fetch from my memory system. So it's measured in ops per byte. So now we have a way to compare hardware, different hardware types to each other. We have a way to kind of quantify the compute and memory required for a specific workload. How do we know which hardware is best for which workload? And for that, we talked about something called the roofline. So that's kind of taking both of those concepts and putting them together on one plot. And turns out that's very useful, especially for deep learning applications where, compute and memory are your main things. You don't really have many control flow things to take into account or things of the like, right? So the main thing is actually the raw compute you have available and raw memory bandwidth you have available. And so the roofline looks like this. We put operational intensity here, and we put performance here. And so, we have a peak performance of a chip, which is just computed by getting the number of multipliers on that chip, multiplying that by the frequency, and dividing by the number of cycles it takes to do each operation, right? And so usually chips are rated with this peak flops per second. Peak flops. And of course, the performance is measured in flops per second. And the operational intensity is ops per byte. So here we would draw a straight line. But the main thing to take into account is that we can't hit that peak performance or even come close to it when my operational intensity is very low, because I will always have the bottleneck of external memory bandwidth. So no matter how much compute I have on the chip, I will always have this bottleneck of I just need to bring data from off chip to on chip. So if I have a very low operational intensity, that means I need to get a lot of data from off chip, and then I would use it to compute very little. So, one operation every gigabyte, for example, in this regime. So we said that, applications that fall here on this specific chip are memory bound, and applications or workloads that are here would be compute bound on this chip. Yeah, the final thing maybe we said about this is that, if I have a workload with the operational intensity here, don't expect it to kind of intersect with the roofline. The roofline is the best possible performance you could get, but usually hardware utilization comes into play, latency, all of these things will make your actual achieved performance somewhere here, right? So always below the roofline. In very rare cases would it actually intersect the roofline. So are there any questions about the roofline before we continue kind of to the next bit? And actually, can people see this? I'm hoping that people can see it.
Yes, we can see this.
Okay, good. All right. Okay, so yeah, a couple of admin things. So the instant access thing should be sorted out. Tell me if it isn't. I realized that I didn't post any office hours. So just if you want to meet, just drop me a line. You can do a private post on Ed, or you can just send me an email and we'll schedule some meeting time. And maybe later I'll put in specific office hours once assignments get a bit more involved. Okay, so now on to hardware efficiency. And I'll start from here again, where we kind of started by analyzing on CPUs and traditional computers, where does the energy go in an addition instruction, for example? We saw that most of it actually goes to overhead, basically fetching memory, doing branch prediction, control, all of that stuff. And then the addition instruction itself takes very little, about 1.5 picojoules in this case, out of 70. And so we talked about that there are many techniques to improve the hardware efficiency. And the first one is to amortize the overhead. And what that means is that I want to make my instructions more complex. And by doing that, I am paying for the same overhead, but I'm increasing the computation that's done, given that large overhead. So we briefly went over some instructions that are now embedded in most GPUs, going from just multiplication and addition as two separate things, now to dot product as a single operation, and finally matrix multiplication, 16 by 16 matrix multiplication as a single operation, bringing down that overhead in terms of percentage from 2000%. Or 200x to 27%, right? So a huge improvement. We also briefly talked about these GPU tensor cores, which do matrix-matrix multiplication. And we compared that to ASICs, like the TPU version 1, which has a single operation that multiplies 256 by 256 big matrices in one instruction. Right? Okay, so today we'll kind of pick up from here and move on to talk about another technique for improving efficiency. And that is by controlling the numerical format and precision. So like I briefly mentioned, we always used to use floating point arithmetic for scientific applications. And that's because floating point numbers, you can easily and quite accurately control the amount of precision you have and the range for these numbers. So they're the closest you can get to representing a real number. Of course, they still have limited precision and range, but it is so the range is so big and the precision is so fine that usually it works very well for scientific applications. And that's actually why most computers support double precision, which is a 64-bit format, and single precision, which is a 32-bit format. And so when deep learning and deep neural networks started, people used single precision numbers for it. They said, okay, we'll use FP32. And what that looks like is drawn here. So you have one sign bit, you have 8 bits to represent an exponent, and you have 23 bits to represent a fraction, or called a mantissa. So is everybody familiar with these numerical formats? Can you maybe just post in the chat, yes, no? Gives me kind of an indication about, okay, yes, lots of yeses. But basically, this is a representation of a number which is, mantissa. Can you see this? Well, I know I'm small now, you can't see me, but basically, mantissa times 2 to the power of exponent, and it has a sign in front of it. So you're representing kind of the number in this scientific format. So when people ran these deep learning applications, they realized, and deep neural networks, they realized, actually, we don't need all of that precision. I can easily reduce my precision and maintain the same accuracy. And so people actually played around with different things there. And the first one is float 16. So float 16 still represents a floating point number, but in reduced precision, which means we use fewer bits for the exponent. So 5 bits instead of 8 bits, and 10 bits for the mantissa. So that, roughly for multipliers, you would have kind of a quadratic growth with the number of bits in your number. So here you would have, much smaller multipliers when you implement them on chip. So 4 times as small because it's quadratic. There is a quadratic relationship. And for adders, you would get kind of a 2x reduction in size and 2x improvement in efficiency. And so reducing these numerics really helps. But then people realized we don't even need all of this range. So floating point numbers give you a lot of range because you can represent exponents. So they went to integer arithmetic and fixed point arithmetic in some cases. So integer arithmetic, the popular formats there are 8-bit and 16-bit. And here we're representing whole numbers only. And so the range is limited by what you can represent in those 8 bits. So you can go from minus, if you have a sign bit, you can go from minus 2 to the power of 7, minus 1, to 2 to the power of 7. If it's unsigned, you can go from 0 to 256 or 0 to 2 to the power of 8 minus 1. So this is typically also much cheaper in terms of circuit area because computing the addition or the multiplication between those numbers, it's like only operating on a mantissa. So that's kind of highlighted here by the color of these bits. The bits are just a single type of bit, which is the mantissa. And as we'll see, it's much more efficient. And so how much more efficient is it, right? So if we look at this plot, it's quite striking because in addition, as we would expect, going from int 8 to int 32, you have a 4x improvement on measured kind of energy cost of adding, 2 int 8 numbers versus 2 int 32 numbers. But in multiplication, it's more striking because, as I said, there's a quadratic relationship when going from, when multiplying 2 numbers. Most multipliers grow quadratically in circuit size. So you have a 16x improvement going from int 8 to int 32. And that's why you will see like new chips like the TPU, for example, they support int 8 as a first class citizen kind of, especially for inference. You will also see kind of in tensor cores and GPUs where they're also focused on reduced precision. I think now they also have FP16 precision in tensor cores, but the first version only had int 8. So, and going from int 8 to FP32, so comparing now a reduced precision integer number to a full precision 32-bit number, we also have very large energy savings. And usually people will mention, quantization. So that's really what, of course, there are many kinds of quantization, but that's usually what happens nowadays in quantization. You go from an FP32 model into an int 8 model. And we'll talk a lot more about quantization later. So, so a question now for you to answer, maybe in the chat or by unmuting. So we looked at multiplication and they saw kind of major improvements in energy when doing quantization and when moving from integer precision to floating point format. But what about addition? So, so why is it when I do, why is it that there is a huge improvement when I do integer addition compared to multiplication? So, so basically what this plot is showing you, and it's just kind of a summarized version of the previous table, is that when I move from int to float in addition, I get a 9x kind of increase in energy. But when I do the same thing for multiplication, I get just a 1.2x improvement in efficiency. So basically, why is floating point addition so expensive compared to integer addition? That's my question. Can anyone venture a guess? So Aman is saying integer add can be done in a single cycle, while integer multiply needs several cycles in itself. That's true. Lakshmi need to take into account different exponents. Yes, so I think everyone is touching upon. So James is saying integer add does not require rounding to the nearest representation of float. Rounding is important, but it's I think it factors less here. But I think people are touching upon the crux of the matter, which is when you're doing floating point arithmetic, you're not just multiplying two mantissas. You also have to play around with the exponents. And actually, when you add two numbers in floating point, you need to first align the mantissas. So they need to, you need to align the exponents. So if you have a number, you know, I don't know, 0.5 or 1 or 2 times 10 to the power of 5 and 5 times 10 to the power of 4. I need that power to be the same before I add the two numbers. So I need to shift all of my mantissas based on the exponents and align and have a uniform exponent before actually adding those numbers. And what that means is that, you know, floating point addition looks something like this, where you know, you have an integer adder somewhere in there, but it's a very small portion of the circuit. You can only perform that integer addition component after you align the two exponents you have in your numbers. So basically, there's so much more involved. While for floating point multiplication, you can do operations on both the exponent and the mantissa. So I think you add the exponents, you multiply the mantissas, you do some shifting in the end, and that's it. But here there's so much, you need to align the numbers beforehand before you do the actual integer add. So integer add is a very cheap part of the operation. Aligning usually requires multiplexers and barrel shifters and things that we will hopefully talk about in the next lecture when we talk more about circuits. And these are very expensive in terms of hardware area and energy. Okay, so we covered kind of the first part. Roughly, how can we gain more hardware efficiency from specialized the overhead and from lower precision, which is often referred to as quantization in neural networks. And usually that's done so far during inference, but people have also looked into using lower precision during training. And if there are no questions, maybe we can move on to the next part about memory optimizations, which are super important as well. Okay, so back to this plot, which I really like because it puts things in perspective. I mean, one thing I should mention at this point is that this x-axis is logarithmic. And we've been kind of comparing numbers and numerical formats to each other and saying, this one is more expensive, no, that one is more expensive. But we've been ignoring that whole bottom part of the plot, which is where the problem actually lies. So does it really matter how much energy my compute takes? It matters much more how much energy my memory accesses take. So this first row here in the memory part shows the cost of accessing a 32-bit number from an on-chip SRAM. So we're not even going off-chip. We're talking about an on-chip cache or an on-chip buffer. So in this case, accessing that 32-bit number is more expensive than multiplying two 32-bit numbers, which is the most expensive arithmetic operation here, right? And that cost grows if your SRAM or if your on-chip RAM is bigger. So if I have an 8 kilobyte SRAM, that's how much it costs. And 8 kilobytes is very small. Usually we have bigger SRAMs. I think you would have megabytes now, and on ML chips, you would go up to 100 megabytes on a single chip, I think. And we'll talk about one chip which has gigabytes, but that's an exception. But usually in the order of tens of megabytes in your on-chip memory. And so if you go up to a 32 kilobyte RAM, accessing that same 32-bit number costs twice as much now, right? And if you go up to a 1 megabyte RAM on chip, we still haven't gone off chip, that same thing, same 32-bit number access now costs 100 picojoules. So clearly memory is the issue, right? And so far we've been talking about on-chip memory. We're not going off chip, we're not going to DRAM, which is way more expensive because now you're paying the cost for getting off the chip, for accessing that other chip, which is powered on its own, and so on. And so if we access that same number from external DRAM or HBM memory or something that's connected off the chip, now it costs way more, 640 picojoules. So what can we do about that, right? So the first thing we can do is to try to get data as close as possible to computation. Basically, the farther the data is, the bigger the RAM it will live in, and that means I need to pay for moving it more, right? So that's called locality. The second thing we can do is reuse. And we briefly touched upon reuse when we talked about convolutions. But basically, once data is close to you, close to your multiplier or where you'll do the computation, make sure to reuse it as much as possible. So these are the two techniques here. And that's part of the reason why we have a memory hierarchy to begin with, right? So in the previous images, I just showed this one block in external memory, and I mentioned, oh, we may have on-chip memory as well. But we have this memory hierarchy basically because the closer you get to your compute, the smaller the chip area you have afforded to you. So you need to now create smaller buffers. So often the stuff that's very close to the compute units is called, register files or private memory or local memory. And these are typically very small. Whereas when you go a bit farther, you have this big block of memory that makes sure that the data is on chip. And again, these are usually called, shared memory or caches or on-chip buffers or on-chip memories or SRAM. And I mean, the reason I'm kind of just labeling all of the different names for it here is that you will hear people use these things interchangeably. And so you should know the terminology. And finally, you would have this chip that's connected, through a PCB usually, but now often in the same package as well. But basically, it's a different chip called external memory, sometimes main memory, global memory, off-chip memory, or DRAM. There's also HBM now, which is a stacked form of DRAM, a stacked version of DRAM. So in most cases, your model lives here. Your deep neural network lives in external memory. I need to bring chunks of it, put it in the shared memory, and then I break that down into my computation unit and put it, in my PEs or my processing elements. And so, so the goal is to kind of get data as close as possible and compute on it there. But the problem is obviously we don't have much storage here. So once we get it that close, we need to make sure that we make the most use out of it before we evict it into a more expensive form of memory, like shared or external memory. Yeah, and this just a quick note that usually, your external memory is in the order of gigabytes, while your on-chip memory usually doesn't exceed kind of tens of megabytes. And finally, registers or register files and private memory, that's in the kilobytes range. So this is an interesting plot because so far what I've been saying is that, the closer you get, the more expensive it is. And that's why, in CPUs, you see this pyramid where external memory is huge. but it has very low memory bandwidth, while the closer you get to your compute, your register file becomes really small, but has extremely high memory bandwidth. And what that means is that it can move data really quickly, but it's a very small thing. On GPUs, this is different, and for good reason. So GPUs are focused on compute. So if you have, hundreds of CUDA cores on your GPU, you can't actually have those CUDA external memory, enough on-chip memory around them. By the way, is my voice breaking up? Or can you hear me okay using this mic?
Just
Oh, sorry. It's fine for me, so.
It's fine, okay. Because I can also hear my own voice in the room, and that keeps breaking up. So maybe it's just the speakers in the room. So someone said it broke up a little bit. Yeah, I don't know. This is a new room. It's IT issues day. So, anyways, so sometimes gets interrupted. Yeah, I think there's something wrong with this room as well. Though this battery is fine. Anyways, I think it's too late, and I'm probably the wrong person to fix it. Anyways, so we'll just have to make do. So yes, so there is this memory inversion phenomenon that happens on GPUs. Because you have so much compute on the chip, you can't actually feed all of that compute without having a huge set of registers to store the intermediate values, to store the operands, and to store the results near the computation. And so that's exactly what you see in NVIDIA GPUs. And that's a reason for its success in kind of computing, in making large computations. Whenever you have lots of compute, you need to feed it with lots of private memory or lots of registers, basically. So Lakshmi, is that clear? Does that make sense? Because you're asking in the chat. Yes. Okay. Yeah. So basically, it's a necessity. You need all of those registers near your multipliers to be able to keep your multipliers busy as much as possible. If you don't have them, then might as well not build those multipliers or CUDA cores in this case. Okay, so we talked about locality, how to get data close to my compute, and we mentioned basically having private memory really close to the computation units. The other thing we want to talk about is reuse. So once data is close enough, we want to reuse it as much as possible. And what that means is that I want to reuse that data either temporally, so read the data once from memory and then use the same data multiple times by the same PE. So in this case, I have memory, I'm loading this 3 into my PE private memory, but then to avoid paying for another movement of a number from memory to my private memory, I keep that 3 there, and I just keep, loading different numbers, multiplying it by that 3. And so basically what I'm doing is, I'm reusing this entry multiple times from a single memory read. And that means I only pay for a single memory read, but I use it for a bunch of computations, which balances the energy overhead for memory and compute a bit. The other data reuse is spatial reuse. So what that means is that when I read something from my memory, I don't just send it to a single PE for computation, I send it to multiple PEs. And then and so I pay for the memory read once, I do a broadcast operation, and then I can multiply it to, different elements in each of those different PEs. So again, if the computation costs much less than memory access, usually this results in a benefit in terms of overall energy utilization. So I'm pasting this example here of temporal reuse and what it means for us when we're actually doing this in practice. So this is a one-dimensional convolution. So I have this activation here and this filter, and I need to sweep that filter across this activation in blue here to produce this result. And so if I just do it naively, if I just take this and sweep it across this, then I would want to multiply, the 0 by the 0, 1 by the 1, 2 by the 2, and so on. And so, so this 0 is loaded at the first time step, but then the next time it's used is way over here. So that means I'm not reusing it. I'm reusing it only at a distance of 5 or 4, maybe it's 4. So a distance of 4. So this kind of defines the term of reuse distance. So how many operations are between the uses of that specific piece of data? And so here is another scheme where instead of having a reuse distance of 4, so every 4 cycles I will reuse that operand, I have a reuse distance of 1, and it's producing the same results, but just in a different order. And so by reorganizing my computations here, I'm able to reuse the 0 multiple times. And so what impact would this have, right, on my hardware system and on my memory hierarchy? So can people venture a guess? So if I have a large reuse distance, what's the problem? Why would I want a smaller reuse distance? James is saying latency. Lakshmi is saying refetch. Alexander is saying need to reload the same data over and over when he's saying cache of data. So, so all of these answers are correct in a way. Less instructions, so not quite less instructions, but so people mentioned this idea of refetching the data, right? So I need to go back to my main memory and refetch the data to put it in my private memory. So that's correct. So that's one reason to have that's one reason why a large reuse distance is bad, because I do the computation and then I throw away the data and I need to refetch it from external memory. Another reason is while this memory hierarchy here shows just one slot or one location for private memory or register, so it has one register per PE. But if I have a large reuse distance, I can also get around that by having 4 registers per PE. So as people correctly pointed out, it's either a cost of refetching that data because I need to dump it back to a cache or some scratchpad or some on-chip buffer, or I would need to design my hardware such that it has a larger set of a larger number of registers close to my PE to be able to cache like 4 operands at the same time to do my computation. So so basically it's bad in one of 2 ways. So here is a spatial reuse example as well. So what we're doing here is, let me see. This picture always confuses me for some reason. Operation ordering 1, right. So we have 4 consumers here. And by consumer, we just mean PEs again. And so, so I'm plotting here the time and what data is being used in which consumer. So if I have, this specific operation ordering, then I can load this 0 once and broadcast it to all consumers. So it's a single memory access. Now, if I have this operation ordering, I have 2 memory accesses to fill those slots of the consumers. And then here, because this reuse distance is now much larger, I need 3 memory accesses to fill those elements, or even 4 in this case. So basically, it's the same idea. Once we have a larger reuse distance, even for spatial reuse, that means we need to do more operations to be able to fill those consumers or those PEs with data. So how can we get those PEs filled with that data? We can use more memory ports. So memory ports just mean a port from which you read memory, right? So here, this illustration is showing like a single memory port. There's one wire coming out of this memory, but I can have 4 of them, right? But each memory port costs actually quite a lot. It's not just a matter of adding a wire, it's a matter of replicating the memory and being able to add all the addressing logic and so on. Or I can do it over time. So I can load 1, 2, 3, then 4 for a very large reuse distance. And in that case, I would just have more latency and more power. And I would need to figure out a way to hide that latency, or it will impact the throughput of my application and so on. So, getting getting a small reuse distance and having data close together is very advantageous for application efficiency. So. And so this idea of reuse kind of sprouted this term of station to keep stationary in your application. So you have your activations, you have your weights, and then you have the results. So the new activations. So inputs, weights, and results or output. And usually people design their compute hardware such that you have one of those things not moving, basically. So they would have them stationary in your PEs. They stay there until I don't need them anymore. So we would achieve a reuse distance of 1 for one thing, whether it's the weights or the inputs and so on. And so here I'm showing a weight stationary organization where I'm loading the weights from my global buffer or my local buffer or some buffer that's away from the PEs. And then I'm multiplying it by the activations in a systolic fashion. And so usually I would have students kind of think about this for a bit and try to fill in the blanks, but let me do the first one at least. So in this case, what activations do we load in which PE and how do we do the computation? Well, we're trying to do a dot product. So we have, A0 times W0 plus A1 times W1 plus A2 times W2 and so on. So in this simple example, I would keep W0 to W7 stored in the PEs, and then I would load the first set of activations, do the addition, and then load the second set of activations and do the addition and so on. So this is weight stationary. On the flip side, my other operand is the input. So can people take a minute to think about what should go in those boxes now? So if my input is stationary here, then what else do I load from external memory? And how do I do my computation in this case? Yeah, I mean, ideally you would have kind of a piece of paper in front of you where you write this out, but if we just, yeah, I mean, it's the same thing basically. So we now have our activations stationary in those boxes, and then we load new weights, we multiply it by the activations, and we do the addition to get the result. So it's the same picture as before, but now when I load in a new set of operands, it won't be a new set of activations, but it will be a new set of weights. And so in what case would I like to have input stationary versus weight stationary? So that's one question. So for example, in the case of convolutions, if people can type in the chat, which is better to have stationary, the inputs or the weights? Okay, so everyone is saying weights. And that's correct, because I'm loading the same weight, I'm multiplying it by many activations. So can people think of a scenario where I would want to do the opposite? I want to load the input and multiply it by many weights. I'm actually trying to think of a scenario as well. Yeah, I mean, running inference on several DNNs and averaging outputs. That's, I mean, I think that's valid. It's interesting because if you run on different deep neural networks, then we're talking about end-to-end running, and usually you can't kind of keep the activations or the inputs cached in your PEs for that long. Usually it's on a per layer basis or even per tile basis, so a piece of a layer. Connect the layer in question into multiple tails, potentially. So again, I would say these larger macro control flow issues of either a model on a model scale or even on a compute primitive like a convolution or linear layer scale, I think that would be less important. Think tiles, think computation tiles that I have within my operation. So a piece, like a dot product, a piece of a matrix multiplication or a piece of a convolution, a compound model with different branches. So again, that you're thinking a bit too macro, I think, everyone, but it's all in the right direction. So I mean, I would say just in linear layers, right? So you have your input, and you usually need to multiply it by different weights. So at batch one, fully connected layer, you would actually reuse your input across all of those weights. Because remember, it's a matrix vector multiplication where rows of that weight tensor are, each row is multiplied by your activation vector. So if you have batch one fully connected layer, that might be a really useful thing to have your activation cached on chip, for example. But the answers are actually very creative and relevant. So maybe at some point we will also discuss tiling in more detail. So in the mapping lecture, I think. And in that case, we will see ways of actually tiling a model such that we are breaking up the computation of two layers at once. But that's for later lectures. Okay, the final kind of stationary is output stationary. So what does that mean? So that means, I have a dot product. I'm multiplying A0, B0 plus A1, B1 plus A2, B2. And there is a partial sum being produced. So first it's A0, B0 plus A1, B1, then it's plus A2, B2, then plus A3, B3, and so on. And so output stationary just means I'm keeping that partial sum cached in my PEs. And that's how I organize it. So in this case, it would look a bit more like this, where we're loading both activations and weights. We're putting them in the PE, we're computing a partial sum, and then we're caching that partial sum, loading A1, W1, and then putting it in the PE, doing the multiplication, and then adding it to that partial sum. And so I will say that most of the architectures that I worked with were either weight stationary or output stationary. So many of the well-known accelerators that we have now are one of those two things. So it's probably worthwhile now to quickly talk about even a different kind of thinking of these computations. And the first one is SIMD or SIMT. So that stands for single instruction multiple data or single instruction multiple threads in GPUs. And what that means is that I have a single instruction and then I load multiple pieces of data and I do that single instruction on them. So add 100 elements. So that's SIMD, right? And usually how it's organized within an accelerator chip is like this. So we would have kind of some kind of memory loading a register file, and then once data is in my register file, it kind of gets broadcast or forwarded to all of the ALUs. The result would be computed, and then the result would be written back in that register file, which can then be used again by all of the ALUs. So what you realize about this architecture is that the main point of contention and point of contact is this register file. And that's part of the reason why GPUs have a very large register file to account, basically to absorb all of that bandwidth of all of those CUDA cores or all of those ALUs or all of those PEs, right? because data will have to pass by that register file before it goes to the next computation in 90% of the cases, right? There are these tensor cores now which work a bit differently. There are more compound instructions where it's not just multiply or add. Obviously, we talked about matrix mul as a single instruction where data doesn't have to go back to the kind of central register file for that core. But in most cases, that's how synchronization happens, or that's how the computation happens. Register file, ALU, register file. So that's one kind of architecture. And by the way, so SIMD, there is this Flint's taxonomy. I don't know if people are familiar with it. If people can see this, so Flint's taxonomy is, we have data on one side and instructions on the other side, and then there's single, multiple, single, and multiple. So there's single instruction, single data, multiple instruction, single data, single instruction, multiple data, so that's SIMD. Yeah, and then multiple instruction, multiple data. So these are different kinds of computers that you can build, and some of them actually refer to computer systems. So usually things in multiple instruction, multiple data, that would be a whole computer system, right? A distributed system that computes multiple instructions on multiple data. A very interesting one is multiple instruction, single data. And that's when you actually have your instructions laid out spatially. So you would have something like, instruction 1, instruction 2, instruction 3, instruction 4, and then you have your data streaming through it in a pipeline fashion. And then you get your result, right? So can people think of some kind of hardware that does multiple instruction, single data? If you can think of one, type it in the chat. Yeah, it's not straightforward because it's not a type of hardware that exists, but it's a hardware you can build. And usually people build that in a custom ASIC or on an FPGA or something like that. So you would lay out your instructions spatially, you would pipeline it, and that's how you can get the efficiency of complex applications that don't really work well in the SIMD fashion. So SIMD is great and GPUs are great when you have literally a single instruction that needs to be performed on multiple pieces of data. So that's true for graphics, where you have a huge image with multiple channels, and you need to perform a convolution on that whole thing. So you have so many independent multiplications and additions that you just need single instructions to operate on all of those multiple data. But when you have a more complex algorithm, FPGAs and ASICs come into play because you really sometimes do need to go to this multiple instruction, single data paradigm. So examples of applications that really need this, things like compression and encryption, and things that need high throughput, but at the same time have complex control flow and dependencies, which can be resolved this way. Anyways, that's actually a sidetrack because now we're comparing the two prevalent architectures of deep learning, and the first one is SIMD. Obviously, GPUs fall into SIMD, fall into SIMD, and then the other kind is called spatial architectures or data flow processing. So that's similar to MISD, multiple instruction, single data. You can think of it that way. But often in deep learning, you would have that instruction be the same. So it's not quite multiple instruction, single data. But the way it's different from SIMD is that if you compare the two images, you no longer have a central register file that I need to write everything back to, right? That's connected to most of my PEs in some way, right? Now, when I compute a result in this ALU here, what I do is that I forward that result to a neighboring ALU, and then that computes another partial result and forwards it, and so on. So that's why it's called data flow processing. Basically, as soon as you compute the data, you don't need to write it back to a central location. You just forward it to the next computation that needs to happen. And here, the next computation happens to still be a general ALU operation. It's either multiply or add, or multiply accumulate still, especially for the kind of things that we're looking at for deep neural networks. But in general, that is quite related to MISD, multiple instruction, single data, where I have this data flow architecture. I have my data flowing through a bunch of instructions laid out spatially on a chip, right? So the prevalent way of using data flow processing or data flow architectures in deep learning is using something called systolic arrays. And so that's what's used in the TPU chip, for example. That's what's used in most of the NPUs in mobile phones. That's what we used at Intel when we built an FPGA accelerator. Systolic arrays are very successful at multiplying matrices or doing convolutions. And so I'll show here two matrices. So here's one, here's another. So A0 to A, so 2 by 2 3 by 3 matrix multiplied by 3 by 3 matrix. How can I multiply it using this systolic array? So just going one step at a time. First, I'm multiplying A0 times B0 here. And then I'm forwarding A0 times B0, or that first partial. No, actually, I'm not forwarding the first partial product. I'm forwarding the first operand, which is A0, to my next PE. So I've already used A0 to multiply it by B0. I'm now forwarding that to the next PE to multiply it by B1. And the same happens here. I already used B0 in my first PE. I'm forwarding B0 to the next PE to multiply by A1. And you keep doing that until you multiply out the whole of the two matrices. So here, again, I'm forwarding B01. B00 made it all the way down here to be multiplied by A20, and so on. So once we kind of get through this, we get the resulting matrix stored into the systolic array, basically. So can people now tell me what kind of stationary is this? What remains stationary during this operation? So it's one of three. It's one of three options. Actually, let me do a poll. So please, no one choose fourth option. Let's say the first option is input, stationary. Second is wait. And third is output, stationary. And fourth is don't choose it. Okay. So yeah, 68% complete. Okay. So basically, as I was describing how data is flowing here, I briefly said, the input is moving from one PE to the other. So that's A0 was moving, from the first PE to the second PE and so on. Whoops. So the A's and the B's are moving. If the A's are the weights and the B's are the inputs, for example, they're both moving across my data flow systolic array, right? So they're both moving to be multiplied by the next thing in the systolic array. And so it's neither input nor weight stationary because those two things are moving. So I think half of the people answered, so a quarter of the people answered each of those, but then half of the people answered output stationary, which is what it is, because I'm keeping my partial sum stored in each PE at any given time. So if you look at this first box, this is the partial sum, and then I'm adding to it something, then I'm adding another thing, and so on. So this is output stationary. And so, yeah, so it's neither input nor weight stationary. You will find, like I said, both output and stationary are quite common. And you'll find weight stationary prevalent in especially mobile chips, where you do a lot of convolutions, basically. So you have a lot of reuse of weights. And so you would store the weights and perform convolutions very efficiently. Okay, so now we touched upon two ways of gaining hardware efficiency. And I realized we just have 10 minutes to go to the third method, which is ineffectual operations. And so we talked about arithmetic, amortize overhead, use lower precision where possible. Talked about memory, locality and reuse are the main things. And never forget that memory is the highest cost in terms of energy when doing a computation. And finally, ineffectual operations. So how do we skip useless operations that don't contribute to my result? So I mean, we're talking about generally dot products, but for example, matrix multiplications. And so what are the kinds of sparsity that we can get? So we can have activation sparsity, which means my activation has zeros. And because we are doing a multiply accumulate operation, any multiplication by zero will result in a zero. So it's always ineffectual. It's inconsequential. It doesn't add to my computation in any way. It doesn't affect the downstream computations. So that's activation sparsity. And usually activation sparsity is achieved either by luck or by activation functions like ReLU, which zeroes out all of the negative numbers, or any activation function that has a big zero output, basically. And then you have weight sparsity. So most of the weight values are usually restricted in range, either through normalization methods or other methods, so batch normalization or other normalization methods. And that sometimes results that, again, by chance, you have some zeros. Some kind of regularizations during training, things like L1 norm, for example, would induce a lot of zeros as well in your weights, would basically shift the training into some kind of minimum in which you have a lot of zeros in your weight tensor. And that's called weight sparsity, right? Or parameter sparsity. And finally, we also have fine-grained sparsity, where zeros are kind of scattered around your activations and weights. And we also have block sparsity. And block sparsity is much easier to deal with, simply because all of our compute chips are SIMD or data flow. So they operate on large chunks of data at any given time. We saw that the TPU operates on 256 by 256 chunks. So if my block is smaller than that, then I can't easily take advantage of the sparsity. For tensor cores, it's 16 by 16 chunks. And in this case, I need my block of zeros to be that big in order to leverage sparsity in a very simple way. Yeah, so usually, as I said, activation sparsity comes from sparse activation functions like ReLU, and weight sparsity can be induced either by regularization or by pruning, which is a method to remove unuseful weights, basically. And then, yeah, so this block sparsity is how I can actually improve my runtime as a result of those zeros. So usually I operate on blocks of this input. So I've been talking about dot products and matrices. So usually if I have a weight tensor like this one, or this is a matrix, I guess, I would take a block of it. So maybe this is 8 by 8 weights. And then I would perform a dot product with those 64 weights times 64 activations. So a 64 times 64 dot product or matrix model or something. And so now if I have fine-grained zeros scattered all over the chip, I can't skip one of those blocks. My smallest computation block here is compute 64 multiply accumulates per cycle. So what I need is actually a weight tensor or a weight tensor, which has zeros organized into blocks of 64 by 64. So it would look something like this. because in this case, I can now skip all of those blocks. So instead of kind of computing all of those computations, I would need to go over all of these blocks of 64 or tiles of 64 in my weight tensor. I can skip this first one, the second one, all of those 0 blocks basically, because I know they will give me a 0. I already know what the result is. And the reason that block sparsity works so well is that I don't need much overhead to realize where the zeros are. I can basically encode those zeros in my matrix using just a single bit. This block is a 0, or this block is not a 0, and I need to do the computation. So my overhead here is a single bit for every 8x8 block that I do the computation for, which means it's like a 1.6% overhead. It's very small, right? And that what does that mean? That also means so that's a 1.6% overhead in terms of memory overhead in what I need to store with this tensor to identify where the zeros are. And then I would have very simple control logic, which takes the single bit and decides to either skip the operation and output an all zeros result, or it actually has to do the computation because I don't have zeros. How is it determined that the block will be 0 beforehand? Samuel is asking, and that's a great question. And I've kind of labeled this by weights so far for that reason. So we're talking about pre-trained weights, and in the scenario where we're doing inference, and I already have the weights trained and I know the results. So it's all predetermined before I do the computation. And so obviously the other type of sparsity is fine-grained sparsity. And until very recent, you couldn't the hardware that supports fine-grained sparsity, right? But NVIDIA is focusing on this, and they started to add them to their NVIDIA GPUs. And their kind of sparsity that they support in their tensor cores is, they support having 2 elements out of every block of 4 can be 0. So it's not quite fine-grained sparsity. It's what's the word? It's like restricted fine-grained sparsity, or it's a specific form of fine-grained sparsity. And so the way they can do that is that they have their own sparsity-aware training that induces those zeros in every block of 4. You would have 2 elements that are zeros and 2 elements that are not. And so, so what's the overhead of this, right? Like it sounds a bit weird, right? But instead of storing that whole, matrix as a dense matrix, you will have lots of zeros. So now you can store it in half the size. In fact, you will have exactly half the entries here as zeros. But you also need to store this companion matrix, which tells me where the zeros are in this block of 4. So it can tell me that the 0 is in, entry 0, 1, 2, or 3. So you need 2 bits to indicate what the indices of those zeros are in my matrix. So we already have not like for the coarse grained sparsity, we computed like a 1% or 1.5% overhead in terms of memory for sparsity. Here I already have 12.5% memory overhead just because of sparsity. But what about the control logic? This also seems like a more complex way of identifying zeros. So how much power savings am I actually getting out of this? And I'd like you to guess again. Relaunch poll, relaunch. Okay, so do you reckon, this is 50% fine-grained sparsity. So in the best case, I'll get 2x improvement. Do you reckon we can achieve that whole 2x improvement in terms of energy efficiency and even just performance, raw performance, or would it be less or would it be more? So yeah, in the best case scenario, I'd get a 2x improvement in my computation because I'm saving 2x of the flops. But so most people answer 2, which is 1.5x. But it was kind of evenly split between 2 and 3. And so I think people realized that, because of these overheads to identify where those zeros are, you will not get the full benefit of skipping those zeros. So the number is actually closer to 1.2x. So I took this from their marketing material, where the performance per watt, depending on the batch size, so basically, if we take an average kind of relative improvement, in terms of raw performance, it's usually less than 1.2x, actually. If you can see here, everything is below 1.2x. It's closer to 1.1x in terms of performance. In terms of performance per watt, it really depends on your batch size. And maybe a fair average would be 1.2x. But in most cases, at high batch sizes, it's smaller than 20% improvement. At low batch sizes, performance per watt can be a bit higher than 20% improvement. But all of this to say that fine-grained sparsity is very hard to take advantage of. And even when people try it and spend a lot of time in making it work, the performance benefits aren't what you'd expect. So here they're shooting for 2x, and that's their upper bound, but they only get 1.2x, or 20% improvement. And so that brings me to the end of this second piece of the lecture. I actually thought would be able to finish the third piece as well, but maybe we'll do that next time. A quick note is that I posted this book. It's an optional reading, but I highly recommend going through it. So these guys, the first reading was from them as well, but then they wrote a whole book chapter to add to their kind of canonical book on computer architecture, which hopefully most of you already kind of went through before. But they added this chapter 7, which is a really nice systematic walkthrough of what it means to move towards those domain-specific architectures with examples of the TPU, which they designed, and other examples as well. I'd recommend kind of at least skimming through that chapter. It's a fun read, and there are lots of kind of nice nuggets of information there as well. I posted the book to the Ed discussion because I realized that our library has an older version which didn't have that last chapter yet. So you can use it for educational purposes, no problem. But yeah, so I'll stop here. Again, I'll hang around for 5 minutes if anyone has any questions. And yeah, I'll see people next Monday, hopefully in person. So that's what I'm excited about that. So, all right, thanks.